Okay, fine, fine. Yes, yeah. Thank you. We'll continue. So I was explaining you about electrophilic substitution reaction. And I just told you what are electrophiles. Electrophiles are electron deficient species, which has less number of electron, whichever is positively charged, okay? Deficient means what? In chemistry, they carry a positive charge. Positive charge means there is more number of protons than compared to electrons. So if electrons are less, then they are electron deficient, okay, which are called as electrophiles. So any positively charged species you can take. Even chlorine, if they carry positive charge, they will come under electrophile. Na with positive charge, they are electrophiles, okay. Anything which carries positive charge. And nucleophile will be something which carries a negative charge like Cl minus and then Br minus, okay, like this. So if they carry negative charge, that means the number of electrons are more in them, they are nucleophiles. So here you are talking about electrophilic substitution reaction. To the benzene ring you have to do. Okay. So we have taken here methyl benzene, that is toluene is taken. And since we need to do addition of chlorine here or any other halogen, if you want, you can take that halogen in the presence of iron. And the medium we have kept is dark because I told you if you take a sunlight, then what happens is this chlorine will go and replace the hydrogen from here. Okay, methyl group they will go and replace. So it won't do the addition into the benzene ring. So that to avoid that problem, we have taken the medium in the dark. Okay, the condition is kept in the dark. So initially, few of the molecules of iron, few of the molecules of iron will combine with chlorine, giving rise to FeCl3. So FeCl3 compound will be formed first, and that will act as a catalyst here. Okay, this will be acting as a catalyst, and this itself will help you to generate that electrophile, because we are doing electrophilic substitution here, no? To generate that electrophile, this will be helpful for us. How it will be helpful? Because you see here iron has how many bonds? 3 bonds, no? It is having 3 bonds with chlorine. Is this correct, students? Is it a stable structure if they are having 3 bonds, 6 electrons? According to Lewis, what does Lewis structure say? How many electrons minimum they should have surrounding them? One element should have minimum how many electrons surrounding them? They have to attain a stable structure. You have learned about Lewis structure in chemical bonding. They should have minimum 8 electrons surrounding them, correct? Yes, so here if you see FeCl3, it is having one bond here, that means 2 electrons. Again one more bond with the chlorine, 2 electrons, and another bond over here, 2 electrons. So the number of electrons they are having is only 6. 6 is not the correct thing, correct, no? 6 is not the correct structure Fe. I'll draw here once again. Okay, so Fe is having 6 electrons. So they require 2 more electrons to complete their octet. So what this FeCl3 will do is it will try to combine with another chlorine molecule, Cl bonded with Cl. And they will try to take all these electrons, Cl and the electrons they will take, and the another chlorine is there, no, that will be left with nothing. Okay, this another chlorine will be getting a positive charge, and this whole Cl will come as a negative one, Cl minus. That Cl minus will be taken by FeCl3 and it will give rise to FeCl4 minus plus Cl plus. So one electrophile will be generated here. Okay, this is similar to where I have explained you about halogenation. Electrophilic substitution reaction, halogenation in first year I have explained you. Okay, so same process it is. First is generation of electrophile, then these electrophile will go and attack the benzene ring. Okay, and here the methyl group which is present over here, the methyl group is ortho-para directing. Okay, it's ortho-para directing. What do you mean by ortho-para directing? Methyl group which is present over here, the CH3 group which is present over here, it is ortho-para, ortho and para directing. Ortho-para directing means when any incoming group comes, okay, when any other group is going to approach this particular compound, they will direct them at ortho position and at para position. Means attack can happen only at ortho position or the attack can happen only at para position. Okay, these positions the attack can take place. So such type of groups are called as ortho para directing group, because you know CH3 group is a donating group. Any donating group will give the electrons to the benzene ring, and there will be more electron density at ortho and para position. Okay, so such groups are called as ortho para directing group. So these electrophile which is generated, either it will go and attack at ortho position. Remember the electrophile, that is your Cl plus which is generated here, this Cl plus which I have generated here, that will go and attack at ortho position, or it will go and attack at para position. So two compounds you can get. Okay, so two compounds we are going to get here. That will be, see, you will have benzene ring, this CH3 as it is. So what you're going to do here is just add one chlorine at ortho position. Okay, that chlorine has come in the place of hydrogen. It will go and attack there, then resonance, all that things happens. But I am not going to do the whole mechanism part, which I've done in first year. If you want, you can go back to that videos and search. You'll be able to find them. Okay, there exactly mechanism also I've explained. So it goes in a similar fashion. It goes in 3 steps. First, there is generation of electrophile. Then this electrophile will go and attack the benzene ring. Electron density is here. Okay, then they will go and attack here, ortho position. Then resonance happens. Then there is removal of proton. Okay, to get the catalyst back. So all that thing happened, but now here we have to just complete the equation and form the product. That much is enough. Mechanism they don't ask. So I just explained you. Okay, so one is at ortho position, one more product will be formed which will be at para position. So CH3 is here. Para position is exactly opposite to CH3. So you will get one is the ortho product and one you will get the para product. Okay, so this is orthochlorotoluene or methyl benzene, and this is parachlorotoluene. You can write even the IUPAC name. If you're writing IUPAC name, then here see, first position will go for chlorine, second position will go for methyl. Again here, first here, second, third, and then fourth. Okay, so it will be 1 chloro, 2 methyl, 1 chloro, 2 methyl benzene. The next one will be 1 chloro, 4 methyl benzene. 4 methyl benzene. Should I repeat this once again? Okay, I'll repeat. I'll go to the next page. See, I'll repeat once again. Listen properly. See, we have taken here methyl benzene. Methyl benzene is taken, that is CH3 group with benzene ring, and made to react with chlorine or any other halogen you can take. Here I have taken chlorine in the presence of iron as a catalyst. Okay, in the presence of iron as a catalyst. So first thing what happens is this iron, few molecules of iron will react with few molecules of chlorine, giving rise to FeCl3. Okay, FeCl3 structure, you know, according to Lewis it is not stable. No? According to Lewis, what is it actually? FeCl3, Lewis acid or Lewis base? According to Lewis, what is this? FeCl3, Lewis acid or Lewis base? FeCl3. Because it's a short of 2 electrons. So they can take electrons. According to Lewis, if they are taking electron, what are they called as? Lewis acid. Okay. Lewis acid. Lewis acid is the one which can accept electron pair, correct? Accept electron pair. And Lewis base is the one who can donate an electron pair. They can donate electron pair. Okay. So here FeCl3 is short of 2 electrons. So they can take 2 electrons. So this FeCl3 will further combine with your chlorine molecule. Chlorine molecule is having chlorine, single bond and chlorine. Okay, this is how the molecule is. So now this FeCl3 when comes in contact with chlorine molecule, since they are short of 2 electrons, what they will do is, they will try to take one whole chlorine atom with the bond. Okay, this whole thing will be taken by them. With the bond they will take it and they will give rise to what? Fe. This is a neutral molecule now here. Okay, FeCl3 is a neutral molecule, will combine with this whole Cl minus. Okay, I'll write here, this is minus because along with the bond it is taken. And this chlorine will be losing that electron. So if anybody loses, they will carry a positive charge. So this Cl minus is taken by FeCl3. So it will give rise to FeCl4 minus plus Cl plus will be generated, which is your electrophile. This is the electrophile which is generated. These electrophile will go and attack the benzene ring. Which position it will go and attack, that depends on what group is present in the benzene ring. So if you see your methyl group which is present here, you can remember this methyl group is an electron donating group. This is electron donating group. So it will increase the density, electron density at ortho and para position. So it is called as ortho para directing group. This you keep in your mind. Okay, you should remember this. If methyl group is present attached to the benzene ring, if any group comes to the benzene ring, they will be directed at ortho position or they will be directed at para position. This much is clear what I said. Okay, now students, yeah. Okay, good. So they will be either directed at ortho position or they will be directed at para position. So you will take one Cl plus, okay, this Cl plus which is there, either you put them at ortho position, this Cl plus, no, because that is the electrophile which is being formed. This Cl plus, either you put them at ortho position or you put them at para position. So there are different compounds which will be formed. One who goes to the ortho position and one who goes to the para position. Okay, so we will get product like that. So we have here this methyl group. Some of the chlorine you put into the only one Cl, okay, don't take Cl2 and put here. It's only that Cl plus which is going there. Okay, electrophile will go and attack here. So this is one product. Another product is where the chlorine will be at para position. One more Cl will be here. Okay, and your CH3 will be exactly opposite to that. So you get ortho position and another one is para position. Is this clear? And from there benzene, what will come out? This Cl is not just going and attacking there. Here, there is hydrogen present. Every time there is hydrogen, no, into the benzene ring. This I have told in the beginning also. And here also, ortho position also there is hydrogen. That hydrogen is actually replaced by the chlorine. So yeah, HCl molecules will come out. So 2 molecules of HCl. Here also I can write this will be 2 molecules actually. Because 1 molecule for ortho, 1 more molecule I have taken for para. Okay, so you get ortho product and para product. Am I clear with this now? Name I gave you just now. See, I'll go back. Name I gave, no, that time. See, 1 chloro, 2 methyl benzene and 1 chloro, 4 methyl benzene. These are common name. Orthochlorotoluene, or you can write orthochloro methyl benzene or parachlorotoluene. These are common name. And down which I have given in green color, that is the IUPAC name. Okay. So names are here, okay? Yeah. I'll continue now. If you want somewhere down, you can write this, okay? Here you see FeCl2. In your book, they have just given Fe and Cl2. They have not explained what exactly happens during the process. What really happens is Fe combines with certain molecules of Cl2. They form this FeCl3. Okay, they form this FeCl3, which is a catalyst. And that being unstable, who is having only 3 bonds, try to attain the octet structure by combining with another chlorine molecule. So they will break that bond, take that whole Cl minus and get converted to FeCl4 minus. Plus this electrophile is generated. This Cl plus electrophile is generated. That electrophile will go and attack the benzene ring. At which position? At ortho position and at para position. Okay, now in that also, if you want to know which is major and which is minor product, let me tell you, this will be always a minor one. Ortho products are usually the minor one, and para products will be usually the major one. The reason is because of steric factor. Okay, steric factor is where if already one molecule is present at the neighboring site. See here, already one CH3 molecule is present. So it will be occupying this much amount of space. It's a small molecule, correct? So here already CH3 is present. So this chlorine to go and attack over here, it is little difficult. So ortho products will be usually less in quantity, and para product will be usually major in quantity, because here immediately next to it is ortho position. There going and attacking is little difficult for them. So they prefer going and attacking at this position, that is para position. Okay. So para is usually a major product, and your ortho will be usually a minor one. Less quantity, and this will be in major quantity. Reason I told you, it is steric factor. Steric means if already one group is present, they won't go and sit in the neighboring group, just to avoid the repulsion. Okay, just to avoid that problem, bond strain and all that. Just to avoid that strain, steric factor, they will go and occupy the place where they can sit aram se. Okay, they can occupy that place properly. Due to that reason, this para is major, and this ortho is minor. Shall I proceed now? Anything else you have to ask? Yes, I'll continue then. Okay, next is a name reaction from hydrocarbon itself. Okay, under hydrocarbon itself it comes. It's a name reaction called as Sandmeyer's reaction. Very important. Name reactions are always important. Wherever you come across any scientist name, okay, those reactions will definitely be asked in your exams. Okay, so you have to concentrate more always for the name reaction. So here Sandmeyer's reaction, this is again for aromatic. Okay, aromatic, that is haloarenes. If you want to prepare haloarenes, this is one more reaction. Just now what you studied was also for haloarenes. This Sandmeyer is also for haloarenes itself. Okay, this is for preparation of haloarenes. Electrophilic substitution is also for haloarenes. Okay, now here in Sandmeyer, what Sandmeyer has done is to do the addition of halogen, see, to the benzene ring, because benzene by nature, they are actually nucleophiles. They are having these bonds, no, you can see here double bond which is present. They are nothing but electrons, no, they are nothing but electrons. So if you want to add halogen here, it's not that easy to directly go and add halogen, because if these are negatively charged and your halogens are also negatively charged, so what will happen if both of them come in contact with one another? It will lead to repulsion. So easy addition is not that possible. Okay, it's little difficult. You have to increase the temperature, conditions apply there. So what Sandmeyer has found the method is to prepare some compound which will make the benzene little like as an weaker, so that addition of any compound becomes easier. Okay, so here Sandmeyer has found a route. It's a different route through which you can do the addition of halogen easily. Okay, so now we will understand that what was the exact reactant he has taken and how the reaction proceed. So what he has taken is, he has taken aromatic amines, because I said here we are doing preparation of haloarenes. So you need something which is having a benzene ring. So he took NH2 with benzene ring, which is called as aromatic amine, and the name is aniline. The name of this compound is aniline. Aniline is aromatic amine. Aromatic because you can see there is a benzene ring. Amine because it is substituted by NH2 group. NH2 group, whenever you find, they are called as amines. Okay, it's a functional group. So this compound he has taken, and he has made this aniline to react with the few more things. Okay, that is sodium. See what he has taken. It is sodium, that I'll write it over here. Okay, sodium nitrite in the presence of acid. I'll take HCl here. In your book, you can find HX is given, so that X can be chloride also. Okay, so here Sodium nitrite. It is not nitrate, it is sodium nitrite. Sodium nitrite crystals are made to react with HCl at very, very low temperature. Okay, this reaction is carried out around 0 degrees Celsius to 5 degrees Celsius. So if you want to convert this into Kelvin, it will be around 273 Kelvin to 278 Kelvin. At very low temperature, this reaction is being done. I'll tell you why low temperature they have taken later. So now when NaNO2 and HCl is made to react, again you can do charge separation here and tell me what will be the product formed. At least that you can do, no? Charge separation. This Na is positive, this will be negative, H will be positive, Cl will be negative. So what will be formed? NaCl will be formed. Yes, one will be NaCl which will be formed. One more thing which will be formed is HNO2. Okay. So here this acid will be formed, and this acid is not very stable acid. You have to prepare during the course of the reaction. You can't prepare and keep it like how we prepare HCl and keep, no? They are quite stable. This is not a stable compound, so it has to be prepared. Whenever you need HNO2, you have to make these two things to react, and only then it will be prepared. Okay, so this HNO2 is made to react with aniline. First, we take all of these and maintain at 0 degree Celsius. All of these will be kept in ice cold, ice bath. We take an ice bath and all the test tubes, all the reactants are mixed in the test tube and they keep in the ice bath at 0 degree to 5 degrees Celsius, okay, to maintain that low temperature. So this compound which is like produced here is made to react with aniline later on. Okay, so see how it reacts. And when HNO2 reacts here, it takes one more molecule of HCl also during the reaction. HNO2 and HCl. So now here you can find there is aniline which is having hydrogen, and there is hydrogen present here also. So when you find hydrogen and oxygen, no students, best way is to remove the water molecule. So how many water molecule can be lost, you think here? Remove the water, because I said mechanism we will not discuss. Directly we will go to product formation. How many water molecule can be removed? You can see how many hydrogen you are able to find here. Take some other color. Yeah, see here. There is 2 hydrogen on this side. Then 1 hydrogen is here. One more hydrogen is there in HCl. And there is 2 oxygen. Correct? So how many water I can remove? 4 hydrogen. That means I can remove 2 water molecule. So 2 water molecule will be lost. Okay, and the remaining compounds, they combine together and they form the product which is this. Okay, I've removed now water. Here, I'll just show you. This hydrogen has gone. This hydrogen also will go out, and this hydrogen also will go out. Okay, so here water molecules will be lost. Remaining is what? I'll just put a tick mark here. See, there is 1 nitrogen present. This one more nitrogen is remaining, and then there is chloride remaining. So that will combine together and gives you this product. Benzene ring is still there. Okay, benzene ring is there here. And then we have nitrogen and nitrogen which combines together. So I'll write as N2. And then there is remaining, that is chloride, Cl. But this N2 will carry 1 positive charge. I'll show you that why it is positive. And this chloride is negatively charged. They are just forming a salt here. And this compound which is formed is called as benzene, because you can see a benzene here. And then there is 2 nitrogen present. And nitrogen is carrying a positive charge. So it is called as benzene. This compound is called as benzene diazonium. Azo is another name for nitrogen. It's a Latin name for nitrogen. Since 2 nitrogen is there, it is called as azo. And why we are ending with IUM? Because nitrogen over here is carrying a positive charge. So it is called as diazonium. And you can see 1 Cl minus present. So it is chloride. Okay, benzene diazonium chloride, which will be an intermediate. And this diazonium chloride is stable only at a 0 degree to 5 degrees Celsius. If you heat this compound, it will decompose. So I said why that temperature is maintained to 0 degree to 5 degree is because this compound which is produced over here will be stable only at that temperature. If higher temperature is supplied to them, they decompose and then you will not be able to do the reaction further. Okay, whatever addition you have to do at this temperature only. Okay, so it is stable, and if you have to do any reaction, you should do at this temperature itself. Okay, so benzene diazonium chloride, it is acting as an intermediate now. Okay, so this intermediate is taken, and this reaction is also called as diazotization reaction. Diazotization aromatization reaction, preparing benzene diazonium chloride. Is this part clear what I told you? Should I repeat this once again? I'll repeat this here. Sandmeyer reaction. Sandmeyer reaction is where Sandmeyer has taken aromatic amine for preparation. Okay, aromatic amine is taken. I said aniline is the compound which he has taken here. Aniline is benzene ring with NH2 group. Okay, and that aniline is made to react with sodium nitrite and HCl. These two things are made to react first. Okay, NaNO2 and HCl is made to react first. When NaNO2 and HCl reacts, they form a salt and one acid is formed, that is HNO2. This acid is important because this acid is doing all the reaction, elimination of water and everything. That takes place through a mechanism. But I said since we are not discussing about mechanism, I told you easily how to remove that water. Okay, so this acid is produced plus NaCl will be produced. NaCl anyways it's a salt. Okay, this acid will go and react with your aniline. Aniline is benzene ring with NH2. Okay, now one more thing to tell you, aniline is a base. Okay, it is basic in nature, and HNO2 is acid. It even combines with HCl, one more molecule of HCl also they take. That HCl you understood because nitrogen carries positive charge later on, so it will take one chloride there, due to which this HCl is included. Okay, now you can remember one more way how to remove the water, because I said this is base and this is acid. When acid and base reacts, you know, it will lead to formation of salt and water. That everyone knows, correct? No, so here I'm telling you aniline is a base and HNO2 is an acid, so you can remove no water from there. So water to remove, here two hydrogen and this hydrogen and this hydrogen plus this oxygen you remove. So there will be removal of two water molecules. Two water molecule will be lost. Rest everything you combine and put it together. Okay, you put this thing together. So I have here benzene ring, then two nitrogen is remaining and they carry a positive charge, and then remaining is one chloride, this chloride group. Okay, this Cl group is there, minus charge, so that minus will interact with the positive charge, giving rise to benzene diazonium chloride. This is our compound now. This you are going to take to prepare haloarenes. Okay, is this clear now what I said? Is it understood, students? Okay, this is an intermediate now. This intermediate we will make use to do the further reaction. Okay, so I'll write that benzene diazonium chloride, benzene with the nitrogen having one positive charge, and then you have chloride. Okay, this compound now we make it to react in the presence of copper chloride, CuCl. If you want to prepare haloarenes having chloride, then you take copper chloride. If you want bromide to be added, you take copper bromide. Okay, so CuCl is taken. CuCl will act as a catalyst here. Okay, this acts as a catalyst and it will try to take this chloride, it will remove this chloride, and a little bit of heating we do. Little bit of heating, why? Because this nitrogen is there, no, that is present. So if you heat them little bit, that nitrogen will escape out. So then remaining will be that nitrogen. I'll just show you, okay, how it happens. You have this benzene ring. And then let me show you that open structure. N2 I have written, no? Nitrogen and nitrogen, how many bonds they form with one another is triple bond. Okay, so this nitrogen is stable here. This nitrogen, which I am putting a tick mark here, this nitrogen is stable. Okay, but see the another nitrogen, how many bonds they are making here? 1, 2, 3, 4. That means they have lost their lone pair. Okay, and when any element loses their lone pair, they will carry a positive charge. So that positive charge which I have put there, no, that's because of this nitrogen. Because they are forming 4 bonds here. See, 1 bond on this side with the benzene. Remaining 3 bonds they are making with the nitrogen. So on the whole, there are 4 bonds. So this nitrogen carries positive charge. Since a molecule is positively charged, it will obviously attract a negative ion. So chloride gets attracted towards this molecule. Okay. Now, when you take CuCl, which is acting as a catalyst here, copper is in +1 oxidation state. You can see here, it is CuCl. That means Cu is in +1 state, and chloride anyways, it is -1. So Cu is in +1 state. So what it is doing is, it will take this chloride. Okay, it will take this chloride and get converted to CuCl2. Okay, it will get converted to CuCl2. And meanwhile, this nitrogen and carbon bond is there, no, that will break down, because here nitrogen is not stable, it is in positive charge. When any element is with positive charge, it is never stable. So they try to make themselves stable by moving out from there. So this bond will break out like this. Okay, see the way I'm breaking, homolytic, free radical, like that. Okay, so this will break down, and this nitrogen will escape out from there. Okay, so it will escape out from there in the form of nitrogen gas. And this radical which is generated here, your benzene, which is having 1 electron here, okay, that one more electron will be provided by this CuCl. CuCl2 is formed, no? So they will provide that Cl back to them. Okay, Cl radical will be provided back, and this will get converted to CuCl back. Because catalyst job is what? Just to help for the reaction to happen. So these two will combine back and give rise to chlorobenzene. Okay, these will combine back and give you chlorobenzene, plus N2 will escape out. Okay, and CuCl will be regenerated back. So this is the final product which is being formed. Okay, so I said when you take benzene diazonium chloride, it will be made to react with CuCl. What CuCl does is, it will take this chloride and go out and form CuCl2. Okay, and here you see that benzene with nitrogen. Nitrogen is having a triple bond, plus it is carrying a positive charge, which is not stable for them. So they will try to attain stability. So to attain stability, they will try to escape out and go out in the form of simple molecule, because like that they will be more stable. So everything in the nature, happens to attain stability. So they will break this bond of carbon and nitrogen. Nitrogen is more electronegative also, so it has tendency to pull that electron, and it will escape out. Okay, in the form of nitrogen gas, it will escape. And this benzene, which is giving you that one radical, that will be combining with CuCl2 is there, no? So one chloride will be provided by CuCl2. Okay, one chloride will be provided, and they will come back in the form of CuCl. Okay, giving rise to chlorobenzene. So if you want bromine, you can take CuBr, like that. But in case of iodide, since iodide is a better nucleophile, you don't have to do any other catalyst. You can directly take benzene compound, this benzene, salt you can take, and then X I've written here because it can be chloride or it can be bromide. So this you can take and directly make it to react with potassium iodide. So during the reaction, nitrogen will escape, this X will go with potassium, and iodine will come and attack here. So you will get potassium with that salt will be formed, and then this will give rise to iodobenzene. Okay, this will be the product for iodobenzene. It's direct reaction with potassium iodide. Yes, okay. Is it clear? Do you want to ask anything, or you want me to explain anything? You can ask now. Or else I'll proceed. And since it is organic, as I've told you, only if you practice, you will be able to understand. Unless you practice, these reactions will never enter your head. Okay, so I'll proceed now. You better practice, and then if you have any doubts, you can anytime come and ask me. Okay, so I'll proceed now. Next is from alkenes. Next preparation I'm doing from alkenes. Alkene, generally, if you're writing, what is alkene? Carbon, carbon, double bond, no? Alkenes are carbon, carbon, double bonded compound. X is any halogen. Here, you're asking about this X, no? Here. This X can be any halogen. This can be chloride, it can be bromide. If you are taking HCl, then this will be chloride. It will go with K. It will go with K. K, X will be formed, plus nitrogen will be formed here, like this. Okay? So this K will combine with, it will form a salt, no? KX. Potassium and then halogen. If it is chloride here, it will be potassium chloride. If it is bromide here, it will be potassium bromide. That will be formed here. And nitrogen, anyways, I told you, it will escape out in the form of gas. This will go out. Remaining will be your iodine, which will combine with your benzene, giving you iodobenzene. This will give iodobenzene. Yes, okay now? Yeah, I'll proceed. Next is, I said, from alkenes. So alkene is generally, I've written here, carbon-carbon double bond compounds are called as alkene. Now to prepare haloalkanes, you need halogen. You need to add halogen here. Okay, suppose if you are preparing only with one halogen, you can add that halogen across the double bond. So for that, what compound we take is hydrogen halide. Okay, HX. Hydrogen halide, generally written as HX, where X stands for any halogen. It can be X, can be fluorine, it can be chlorine, it can be bromine, or it can be iodine, anything. Okay, so we are going to add this HX across the double bond. And you know, between H and X, they are polarized. They themselves are polarized, no? Because even though it's a covalent bond, being halogen being more electronegative, it will be partially negative, and this hydrogen will be partially positive. So if you take this polarized compound towards a carbon and carbon which is unpolarized, they will also get polarized. Okay, now if I get this separated charge ones towards this carbon-carbon double bond, carbon-carbon double bond also is electrons, no? So electron cloud will get disturbed. So then this carbon, any one carbon, okay, depends in which direction they are coming. One carbon will carry negative charge and one carbon will carry positive charge because of this bond shifting to one side, okay. I've just taken that. Double bond means it is nothing but electrons, pi electrons. So pi electron cloud will shift to one carbon and one carbon will lose it. So they will carry positive charge. Did you follow what I said just now? When you take hydrogen halide by themselves is polarized, okay. One carries positive charge and the other one carries a negative charge. So if you bring something which is polarized towards this compound, I'll erase this now. See, initially this is how it was. So if you bring something which is polarized towards the carbon-carbon double bond, this electron cloud is there, no, this pi bond is there, no, that will get disturbed. Okay, so it will shift. This electron cloud will shift. Okay, if you want, I'll show it down here like this. See, if they shift, no, imagine that I've shifted that. So that bond I've shifted. So one carbon will get negative charge and this carbon will get positive charge. And here you are having H and then X. One is negative and one is positive. Okay. Now you can add them. So when you are adding, this positive will go towards which one? This one. Okay. This negative will take the positive and this negative will go towards this carbon. So what will be the product formed you see generally? This is general equation which I have written. So it will be like this. Single bond here, and then this carbon which is positive takes the halogen, so one halogen will come here, correct, and then one hydrogen comes here. So it's the addition reaction. Addition happens only if there is double bond. Only across a double bond addition can happen. Otherwise, if it is single bonded, saturated compound can only undergo substitution reaction. Let me make that very clear to you. If they are single bonded compound, it can only undergo substitution. Okay, but if they are double bonded compound, it can either undergo addition as well as substitution. Okay, this can undergo addition and even substitution is also possible for them. But here, since pi bond is available, it is easy for us to add and it undergoes addition reaction. Is this clear, students, what I said just now? It's simple because you have learned even in first year. I've repeated so many times in hydrocarbon. When I was explaining you alkene, when I was explaining you alkyne, that time you have studied all of this. I don't know how many of you really remember it. Now I'll take one example for this. Okay, instead of writing the general equation, I'll take an example. Ethene I'll take as an example. So let's take ethene, CH2 double bonded CH2. Instead of taking HX, I'm taking HBr here. I'll take HBr. Okay, HX was general, no? Instead of X, it is Br now. Now when you add, addition can happen anywhere because I said it's and it is symmetrical. So anywhere if you add, the product will be same. You can add that H here and you can add Br here. Okay. So if I add H on that side, then what will I get? Double bond will break, no? Just now you have seen here, see, the double bond breaks. They get converted into single bond and one Br comes here, one H comes here. Okay, I'll add like that only, the way I have shown here. One Br comes here, one H comes here, double bond will go out. Okay, double bond will go out. So what you will get? CH2, single bond Br and single bond. Here it will be single. Okay, this will turn out to be single because this bond has gone. And then CH2 was there, one more hydrogen you are adding, so it will be CH3. If you do the addition the other way, if you add hydrogen here and bromine here, that also will be same because you can write the name and you will understand. With the name, you can understand the product is actually the same thing. See, if I name them, it is 1 bromo, 2 carbon, it's 1 bromo ethane, no? Now imagine if I do addition in this way. I will add hydrogen here and if I add bromine on this carbon, then you see what will be the product. Product will be like this. CH3, correct? A single bond, CH2 and Br will come here. If you name them, even this is 1-bromoethane itself. This is also 1-bromoethane. So you see the product is same. So if your alkene is symmetrical, anywhere you add that hydrogen and bromide, the product will be same. Okay. Symmetrical alkene. Symmetrical means what? If I take a line and draw across a double bond, I will be getting equivalent group on both the side. You see here, one side I'm getting CH2, this side also I'm getting CH2 and the other side also I'm getting CH2. So if you get same group across the double bond, they are called as symmetrical alkene. This is called as symmetrical alkene. So to symmetrical alkene, if you are adding this unsymmetrical compound, that is HBr, anywhere you add, the product is same. Okay, the product will be same. But when you are adding to a unsymmetrical alkene, the product will differ, which has to be like you have to find out through Markovnikov rule. That I'll tell you afterwards. This much is clear what I have explained. You tell me. Is this part clear to everyone? Or you want me to do any repetition? You just let me know. Fast, quickly. Clear? Understood. Okay, very good. Fine.